Hey everyone! Welcome to our PyTorch tutorial. Get ready to jump into the thrilling world of deep learning with one of the most dynamic machine learning frameworks out there. In this course, we're going to cover the essentials of PyTorch, from creating and manipulating tensors to implementing neural networks, all while engaging you with coding exercises to solidify your skills. Plus, you'll find a link in the description to our GitHub repository where you can grab all the code we'll be using along the way. Make sure to subscribe for more exciting content. Now, let's get started. Welcome to our PyTorch tutorial. Today, we're diving into the exciting world of deep learning, specifically focusing on getting familiar with PyTorch, one of the most powerful and flexible machine learning frameworks out there. I'm thrilled to walk you through the basics of PyTorch, which will lay the foundation for building your own neural networks. So, if you're ready to start your deep learning journey, let's get into it. First things first, what is PyTorch? PyTorch is an open-source machine learning framework that has become particularly popular for its ease of use and dynamic computation graph capabilities. Developed initially by Facebook, PyTorch has become an essential tool for researchers and practitioners. Its popularity can be attributed to its intuitive and flexible nature, allowing for easier experimentation, particularly in research settings. You might have heard of alternatives such as TensorFlow, JAX, or CAF. Each of these frameworks has its strengths. TensorFlow is often regarded as more production-ready, while PyTorch excels in research environments. The great news is that once you become proficient in one of these frameworks, transitioning to another shouldn't be a daunting task, as many concepts are interchangeable. At the University of Amsterdam, we've chosen to utilize PyTorch specifically for its widespread adoption in the research community, and the fact that many papers published today offer implementations in PyTorch. We aim to create a tutorial that covers the essentials you'll need for practical applications, while also giving insights into how PyTorch functions under the hood. Over the coming weeks, we'll be exploring new features as they come out, so stay tuned. Before we jump into coding, let's make sure we have our environment set up correctly. If you're running this notebook on Google Colab, you're in luck. Most of the libraries you'll need are pre-installed. However, if you plan to run it locally, ensure you have our DL2024 environment set up and activated beforehand. In this section, we will focus on the essential libraries that facilitate our deep learning tasks. The initial imports start with standard libraries such as OS and Math, which provide basic functionality for file handling and mathematical operations, respectively. We then bring in NumPy, a vital library for numerical computations, enabling efficient manipulation of arrays and mathematical functions. For visualizations, we employ Matplotlib, Pyplot, a powerful plotting library, which is initialized with the %matplotlib inline command to display plots directly in Jupyter notebooks. We enhance the visual quality of our plots using setmatplotlib formats to ensure they are saved in high-quality formats like SVG and PDF. The toRGBA function from Matplotlib, colors, also aids in converting color specifications. Additionally, we use Seaborn, a library built on top of Matplotlib that simplifies the creation of visually appealing statistical plots, and we customize its settings with SNS, set, for better aesthetics. Finally, TQDM, Notebook, provides us with a progress bar that improves the user experience by visually indicating the progress of running computations, facilitating a more efficient workflow during long processes. In this segment, we will import the PyTorch library and check its version to ensure that our setup is correct. The first line, import torch, loads the PyTorch library so that we can utilize its powerful features for tensor computations and deep learning. This is essential, as all subsequent operations and models will rely on the functions and classes provided by PyTorch. The second part of the code, print, using torch version, serves a dual purpose. It not only confirms that we have successfully imported the library, but also shows the version of PyTorch currently in use. By accessing Torch version, we retrieve the version information, which is crucial for compatibility with various libraries and functionalities. It is important to be aware of this version, especially if you encounter any discrepancies or need to implement features that may only be available in newer releases. If you find a version lower than 2.3, you might need to adjust your environment to ensure compatibility with the latest features. Thus, this code not only sets the stage for our work, but also ensures that we are properly equipped to use PyTorch effectively. Setting a random seed is a fundamental practice in programming, especially when working with algorithms that produce random outputs. In this case, we use the function torch manual seed 42, which is part of the PyTorch library, a popular framework for deep learning. By specifying a seed value, in this case 42, we ensure that the sequence of random numbers generated by PyTorch will remain consistent across different runs of our code. This consistency is crucial for reproducibility, allowing other developers and researchers to replicate your results and verify your findings. When you set the random seed, every subsequent call to a random number generating function will yield the same result, providing a stable environment for debugging and comparison of different models or training processes. This means that if you're experimenting with hyperparameters or neural network architectures, you can be confident that any changes in your results are due to those adjustments rather than variations in random number generation. Overall, establishing a fixed seed creates a controlled setting that can significantly enhance the reliability and interpretability of your experiments. In this section, we'll explore the creation of tensors using various methods in PyTorch. First, we see the initialization of a tensor with uninitialized values using torch tensor 2, 3, 4. This creates a three-dimensional tensor with the shape of 2x3 x4. The specific values in this tensor are not set, which means they will contain arbitrary data until explicitly assigned. After its creation, we print the tensor to visualize its state. Next, we demonstrate how to create a tensor directly from a nested Python list using torch tensor 1, 2, 3, 4. This allows for a straightforward conversion of structured data into a tensor format. The resulting tensor retains the structure and values present in the list, showcasing how easily PyTorch integrates with native Python data types. Finally, we utilize torch rand 2, 3, 4 to create another three-dimensional tensor, but this time it is filled with random values uniformly distributed between 0 and 1. This method is particularly useful for initializing weights or testing models, as it generates tensors quickly with diverse values, ensuring that our neural network starts with variability. We print this tensor to observe the generated random values within the specified dimensions. In this section, we will explore how to check the shape of a tensor in PyTorch. The first code snippet demonstrates the use of the shape property and the size method to retrieve the dimensions of the tensor x. By assigning x_shape to the variable shape, we obtain a quick overview of the tensor's structure, which is then printed to the console. Similarly, using xSize, we fetch the same dimensional information and print it as well. Both methods yield the same result, providing flexibility in how one prefers to access tensor dimensions. Moving on to the second code snippet, the focus shifts to unpacking the size of the tensor into individual dimensional variables. By utilizing xSize, we can directly assign the dimensions to dim1, dim2, and dim3. This breakdown allows for easier manipulation and understanding of each dimension, which is particularly beneficial when designing more complex models. Accessing individual dimensions in this manner can enhance clarity and facilitate operations that depend on specific tensor configurations. In the following example, we demonstrate how to convert a NumPy array into a PyTorch tensor. First, we create a NumPy array named npr with specific values, and then utilize the torch from numpy function to convert it into a PyTorch tensor. This showcases the seamless interoperability between NumPy and PyTorch, allowing you to leverage existing NumPy data in your deep learning workflows. We then print both the original NumPy array and the newly created PyTorch tensor to visualize the conversion. Next, we look at the inverse operation, converting a PyTorch tensor back into a NumPy array. Here, we first initialize a tensor using torch arrange, which generates a tensor with a range of values. Then, we call the numpy method on the tensor to perform the conversion. This step highlights how easy it is to switch back and forth between these two data representations, which is essential for those who are accustomed to using NumPy. Finally, we address a key consideration when working with tensors on a GPU. If a tensor is allocated on a GPU, it cannot be directly converted to a NumPy array. Instead, we must first move it to the CPU using the CPU method before invoking numpy. This ensures that the data is in the correct location for proper conversion, illustrating the neat functionalities provided by PyTorch for handling different hardware configurations. Let's explore some fundamental operations in PyTorch, which enable flexible tensor manipulations similar to those in NumPy. First, we create two random tensors, x1 and x2, each with a shape of 2 by 3. By adding these two tensors together using the plus operator, we generate a new tensor, y, that contains the element-wise sum of x1 and x2. When you execute this operation, you will observe that y reflects the combined values of the corresponding elements from both input tensors. Next, we delve into in-place operations using the add method, which allows you to modify a tensor directly without creating a new one. In the second block, we again initialize x1 and x2 and display their values before the operation. When we invoke x2, add x1, we effectively add the values of x1 to x2 directly, altering x2. Finally, we print the tensors after the in-place addition to see how x2 has been updated, while x1 remains unchanged. This illustrates the concept of in-place operations, which can be efficient in terms of memory usage. In this section, we will explore how to manipulate tensors in PyTorch, focusing on reshaping and dimension permutation. First, we create a tensor x using torch arrange 6, which generates a one-dimensional tensor containing 6 elements. When we print this tensor, it reveals its initial arrangement. Next, we utilize the view2,3 method to reshape x into a two-dimensional tensor with 2 rows and 3 columns. This method is essential for preparing data for various machine learning operations, as it allows for greater flexibility in how we organize our tensors. After reshaping, it's crucial to understand that sometimes we need to rearrange the dimensions of a tensor rather than just changing its shape. We achieve this with the permute method, where we swap the tensor's dimensions. In this case, by permuting the dimensions from 1 to 10, we effectively swap the rows and columns of our already reshaped tensor. This operation is particularly useful when specific ordering of the data is required for certain computations, or when aligning it with the expected input of a model. In this section, we will explore how matrix multiplications are performed in PyTorch using the torch matmul function. First, we create a tensor x using torch arrange 6, view2,3, which generates a 2x3 matrix with values ranging from 0 to 5. This is shown as x in the output. Next, we initialize another tensor w with a 3x3 structure containing values from 0 to 8, displayed as w. The heart of our operation occurs when we apply torch matmul x w, which computes the matrix product of x and w. This function not only supports standard matrix multiplication, but also accommodates higher dimensional tensors through broadcasting. The result of this multiplication is stored in the tensor h. Finally, when we print h, we obtain a new tensor that reflects the accumulated values resulting from the multiplication of x and w, demonstrating the power of matrix operations essential in neural networks. Hence, understanding how to manipulate these tensors effectively can greatly enhance our model building capabilities. In this section, we will explore how to effectively use indexing in PyTorch tensors, similar to NumPy. The code begins by creating a tensor x using the torch arrange function, which generates a sequence of numbers from 0 to 11 and reshapes it into a 3x4 matrix. This tensor acts as our dataset for indexing examples. The first indexing operation, x1, retrieves all rows from the second column of x. This demonstrates how to extract a specific column, which is crucial when you need to focus on particular features of your dataset. Next, x0 accesses the first row, illustrating the capability to isolate individual entries in your tensor. Further, the statement x, 2, minus 1, showcases how to select multiple rows while simultaneously targeting the last column. This is particularly useful when working with datasets that require retrieving data across various dimensions. Finally, x1, 3, retrieves the middle two rows entirely, allowing for complete visibility into a subset of the tensor. Each of these operations highlights the intuitive nature of indexing in PyTorch, which facilitates the manipulation of data as your tasks become more complex. As we wrap up this introduction, remember that mastering these foundational concepts within PyTorch is crucial for your journey into deep learning. The framework is powerful and provides a level of control and flexibility that is unmatched. As you continue to explore the world of neural networks, you'll find that the ability to manipulate tensors, perform mathematical operations, and build complex models will become second nature. Stay tuned for our next tutorials, where we will dive deeper into building neural networks using PyTorch. If you have any questions, feel free to drop them in the comments below. Thanks for watching, and let's continue this exciting journey into deep learning together.